Welcome, everyone. Today, we are stepping into the dawn of the agentic era. We are moving beyond a I that just chats into a I that thinks, remembers, and acts. Let's get started. To understand the dawn of the agentic era, we first need to define what an AI agent actually is. We are moving away from static large language models that simply generate text in response to a single prompt. Instead, we are entering a phase where AI acts autonomously to achieve specific goals. Why does this matter? Because real-world workflows require multi-step processes and adaptability, not just one-off answers. How do we achieve this? By embedding a language model inside a continuous loop of reasoning and action. As we deep dive into this topic today, we will focus on the three foundational pillars that make this possible: planning, memory, and execution. These internal components are what transform a reactive chatbot into a proactive, intelligent problem solver. Looking at our flowchart on the screen, you can clearly see this technological evolution. On the top path, representing a traditional static LLM, the system takes an input and generates text. It's a linear, one-way street. But look at the bottom path, representing agentic AI. It is cyclical and iterative. The agent plans its approach, executes actions using external tools, and then remembers or reflects on the outcome. This feedback loop feeds right back into the planning phase, allowing the system to adapt dynamically over time. Now let's explore the engine that drives an agent, the React framework. React stands for reasoning and action. What this means is that the agent alternates between internal thinking and concrete external actions. Why is this pairing so crucial? Because an AI that only reasons never actually does anything in the real world, and an AI that only acts without thinking cannot adapt to errors. How does it work in practice? The agent generates a thought about what to do next, takes an action like calling a tool, and then receives an observation or feedback from the environment. In our deep dive, we see that this is a recursive cycle. The reasoning trace itself becomes part of the agent's evolving state, giving it the context needed to reflect and make smarter choices on the next iteration. Let's trace the flow on this diagram. We start at the top with a user request. The agent doesn't just blurt out an answer. It moves into the thought node to reason about the problem. This leads to an action, like searching a database. The result of that action is the observation node. Notice the arrow looping back from observation to thought? That is the reflection mechanism. The agent evaluates the feedback, thinks again, and continues this loop until it is confident enough to break out and deliver the final answer. Our first major internal component is planning. What is planning for an AI? It is the ability to decompose a massive complex objective into small tactical sub-goals. At a basic level, we use techniques like chain of thought prompting to force the AI to show its work step by step. Why do we do this? Without a plan, large language models get overwhelmed by complexity and are highly prone to hallucination. How do advanced agents plan? They use frameworks like tree of thoughts, exploring multiple potential paths simultaneously. In a deep dive, this means the agent acts like a chess player, evaluating competing strategies, pruning away bad ideas, and carefully sequencing its next moves before committing to an action. This tree diagram perfectly illustrates task decomposition. At the very top, we have the high-level goal, which might be something vague like write a research report. The planner breaks this into sub-goal 1, say gather data, and sub-goal 2, draft content. Those sub-goals are then broken down further into granular action steps. By navigating this tree, the agent transforms an impossibly large prompt into a series of manageable, highly targeted executions. Next, we move to memory. What does memory mean for an AI agent? It is the critical capability to store information and recall it to inform present decisions. The basics involve splitting this into two types: short-term memory, which tracks the immediate conversation or task session, and long-term memory, which persists across different sessions. Why is this vital? Because an AI without memory suffers from amnesia at every step. It would repeat mistakes and lose track of the goal. How do we build this? We use message arrays for short-term context and sophisticated vector databases for long-term semantic retrieval. Diving deeper, memory is the bedrock of adaptive learning. It allows the agent to recall what tools failed yesterday so it can choose a better path today. Here we see the memory architecture of an agent. In the center, the agent core communicates bidirectionally with two distinct storage systems. On the top, the short-term cache holds the current context, what the user just said or the tool just retrieved. returned. On the bottom, the long-term vector DB stores past experiences and facts. By querying both systems simultaneously, the agent grounds its reasoning in both the immediate situation and its historical knowledge base. The final pillar of the agent is execution. What is execution? It is the agent's ability to reach out and actually manipulate the external environment. At a basic level, this involves using an action space containing things like web search APIs, calculators, or code interpreters. Why do we need this? Because a language model on its own is a static predictor trapped inside its training data. Tools give it hands and eyes. How is this achieved? Through a mechanism called function calling, where the agent outputs structured requests that trigger your code. In our deep dive, we realize that execution is the bridge between thought and reality. It converts natural language intent into concrete system-level effects, and then captures the results to feed back into the agent's brain. This flowchart demystifies the execution process. On the left, the LLM generates an intent. This intent hits a tool router, which acts as a switchboard. Depending on the need, it routes the request to a web search, a database, or a code interpreter. These external systems do the heavy lifting and return their output to the observation node. Finally, that observation flows right back into the LLM, closing the loop and allowing the agent to analyze the data it just fetched. We have looked at planning, memory, and execution. Now let's look at the unified architecture. What happens when we put it all together? We get a fully functioning agentic system. Basically, the LLM serves as the central brain, acting as an orchestrator for these disparate modules. Why must they be unified? Because planning needs memory to know what worked, and execution needs planning to know what to do next. They are deeply interdependent. How do developers build this? They use state graphs to route data securely between these components. Diving deep, modern enterprise systems use hierarchical state machines. This means the agent operates inside strict, defined superstates, ensuring that while it has autonomy, it cannot violate core safety policies and guardrails. Look at this central hub model. The LLM core sits right in the middle, represented by the circle. It maintains continuous two-way communication with the planning module, the memory module, and the execution layer. The user feeds inputs directly into the brain, which consults its plan, checks its memory, utilizes its tools, and eventually produces the final output. It is a highly integrated, dynamic system. A truly agentic system doesn't just follow a rigid script, it exhibits adaptive behavior. What does this mean? It is the ability to self-modify actions based on changing conditions. At a basic level, if an API call fails or a search returns no results, the agent doesn't just crash and throw an error to the user. It reflects, catches the error, and tries an alternative approach. Why is this necessary? Because the real world is messy and unpredictable. How does the agent adapt? It constantly compares its current state to the desired goal. If there is a gap, it changes the plan. In a deep dive, we see this as a run, measure, refine loop. The agent is practically mimicking human trial and error, becoming smarter and more resilient with every iteration. This flow diagram highlights the self-correction mechanism. We start at execute action, moving into a decision gateway, check outcome. If it's a success, we smoothly transition to the next step. But if it's a failure, the system routes to reflection and error logging. Here, the agent reads the error, moves to adjust plan, and loops all the way back to execute action with a brand new strategy. It's a continuous cycle of resilience. Finally, let's look at the future of the agentic era. Multi-agent coordination. What is this? It is the evolution from single isolated agents to entire teams of specialized AI workers. The basics involve a supervisor agent delegating tasks to specific experts like a researcher agent or a coder agent. Why make it so complex? Because a single agent eventually hits a cognitive limit. Dividing labor mirrors the efficiency of human organizations. How do they collaborate? Through hierarchical networks or peer-to-peer swarms, utilizing shared memory protocols. In our deep dive, we realized that the supervisor isn't just passing messages. It evaluates sub-agent execution, synthesizes the context, and ensures the global objective is met safely. This is the true power of the agentic era. Our final diagram shows a multi-agent hierarchy. The supervisor agent at the top acts as the project manager. It distributes tasks to 3 specialized workers: the researcher, the coder, and the reviewer. Notice how all 3 of these specialized agents feed into a single shared memory database at the bottom. This ensures that while they work independently on their specialized tasks, they all share the exact same global context and data.